Alright, welcome everybody. So today I'm going to talk to you about radioactivity and about what it means to be a stable versus an unstable nucleus. We'll try and get into natural transmutation and maybe a little bit about artificial transmutation, depending on how quickly I can go through this and still make it understandable. So radioactivity, basically what it means is that the nucleus of an atom is unstable. And if a nucleus of an atom is unstable, what it generally will try and do is it will try and change into a more stable form. Now that seems pretty general. What determines if the atom is actually stable or unstable? Well, what determines it is the ratio of protons to neutrons, or neutrons to protons, either way. And what you'll see is that there is this range within the periodic table called the belt of stability. And I have a picture of that I'll show you. That will really tell you, well, is the atom going to be stable or radioactive, unstable? And generally, if you're a small atom, we're talking about atoms 1 through 20, if you're a small atom about 1 through 20, then your ratio of protons to neutrons should be 1 to 1. If you're a larger atom, then what we see is that the ratio of protons to neutrons is 1 to about 1.5. And this visual, the belt of stability that I'll show you in a second, that one actually kind of illustrates it for you, and you can see what that looks like. Now, what does an atom do when it's unstable? To become more stable, it goes through something called a transmutation. Sounds fancy. Basically what it means is that the atom, its nucleus, will change into a different atom. And how does it undergo this transmutation? Well, this is where it releases or emits energy and some particles. So what you'll see is that there will be this release of energy, and there's also the release of some kind of particle. So when somebody talks about something being radioactive, what they're really saying is that the nucleus is unstable. And that unstable nucleus, it's emitting energy, and these particles, these high energy particles, they're moving with quite a large velocity. And what ends up happening is that they're very damaging to people and to any sort of living organism. And it causes DNA damage and sickness. And that's really what the issue is with radiation and why it becomes so dangerous. Now, just so that you know, this transmutation, sometimes it's called decay. Sometimes it's called natural decay as well. All right, so let's look at the belt of stability here. The belt of stability, they show you the 1-to-1 proton to neutron ratio down at the bottom here. And we can see that those first 20 or so atoms fall right within that straight line of 1-to-1. And then as the atom gets larger and larger, the ratio becomes 1.25 to 1, 1.4 to 1, and 1.5 to 1. If you think about an atom, what's inside its nucleus? Inside the nucleus, what we have are all these protons. Those protons, they're naturally repelling each other. Yet there's this strong force, as it's called, that's holding together the nucleus and overcoming those repulsions. But there has to be a certain ratio of protons to neutrons, or the repulsion becomes too great, and the atom will try and change into something else to reduce that repulsion, and so that the strong force will be strong enough to hold the atom together. Now let's talk a little bit about natural decay. And the definition of natural decay, or natural transmutation, this is where an atom, and sometimes they'll call the atom nuclides, so where a nuclide changes into a different element, sorry, misspelled that, a different element on its own. And it does so by emitting certain particles. And we can see these particles highlighted from your reference table in Table O here. They give you these different particles. If we go through them, we have alpha particles, beta particles. This is from the old reference table. They actually took out the word electron. They used to have the word electron. Now they took that out. Gamma radiation, which normally comes off with these other types of emissions as well. And positron. They also throw in a neutron and a proton, which we'll use in nuclear chemistry, but not for natural transmutations. The ones I highlighted in red, those are the ones that come off and are used in a natural transmutation. Now, let's talk a little bit about these particles and their details. The charge of an alpha particle is +2, and I just want to bring you back to the previous slide here. If you look at this notation here, you should highlight this. When we have our notation, we have the symbol. Up here we have the mass, and down here we have the charge. So an alpha particle is +2. A beta particle has a charge of -1. A positron is like an anti-beta particle, and that one has a +1. The mass of a beta particle is essentially 0. There is some mass to it. The mass of a positron is also 0, and the alpha is the most massive one at 4. The gamma radiation, that is the same as a gamma photon, and that one has no mass or charge. So here we have another chart showing you alpha, beta, and gamma radiation. And what I really want to draw your attention to for this slide is the penetrating power. So if I were to have an alpha particle source, the same ones that Rutherford was using when he did the gold foil experiment, the penetrating power of an alpha particle is pretty low. In fact, it won't really penetrate your skin to any great degree. People working with alpha emitters, as they're called, they don't really wear that much protective gear, although they will, check themselves for radiation exposure. Beta is 100 times more powerful. And then gamma is 10,000 times more powerful than alpha. And I'll show you a video in class where we see these radiation types penetrating through different metals, and it's pretty miraculous to see the difference between them. So you should know the difference between these. It's important. Now also what they sometimes ask you about is the deflection of these particles in an electric field. And so if we have a beta particle, that beta particle is negatively charged. And because it's negatively charged, it'll attract to the positive electrode. Neutrons and gamma radiation will go straight through. They don't have any charge. And then alpha particles, positrons, and protons, those will be attracted to the negative terminal. Just like we did with J.J. Thomson's experiment with the magnet, where I was able to bend that ray of electrons, we could do the same thing and have a detector, and the detector will register when a particle hits it. Now, just to put this into perspective, when we think about gamma radiation, it is one of the most energetic type of radiation that you could come across. It's more energetic than X-rays. And this is why people are so concerned with radiation and radioactivity. Because when you have these gamma rays that are emitted from a radioactive source, they're really dangerous and they need to be contained. And as we go over the pros and cons of radioactivity, I want you to keep that in mind about how powerful a gamma ray is. Remember, we talked about the wavelength and the frequency, and so you can see that the gamma radiation has a really small wavelength. It almost exists as an energetic particle in a sense because the wavelength is so small. Now I just want to go over one more thing with you for this video, and that's writing these decay equations. We talked about natural decay briefly before and defined what it was, but what does the decay equation actually look like? How does a particle decay? And here I give you an example, and all it really is about is the math. This is our starting particle over here, and I can highlight this from the table here. They're in alphabetical order. Here it is. It's a little bit blurry. And it's saying that it's giving off a B+. A B+ is a positron. So I have my beta positron. It has a 0 mass and a +1 charge. And so this calcium atom that has a mass of 37 and an atomic number of 20 is giving off these beta particles naturally. Now, what does it change into? Well, now we can just do the math. The beta particle has a mass of 0. So what plus 0 would give me 37? Well, a 37. So the mass doesn't change when it undergoes positron decay. However, the atomic number 20, something plus 1 would give me 20. That would be 19. We can see that the calcium has changed into potassium. So it actually underwent this transmutation where we have this natural decay and calcium was transformed into potassium. Now, how did that happen? Well, if we count the number of protons and neutrons over here, this one had 20 protons and 17 neutrons. Over here, we have 19 protons and 18 neutrons. So what did we do? We took a proton and we changed it into a neutron. And that's exactly what happens when a beta particle that's a positron is emitted. Let's look at krypton 85. So first I need to go to the periodic table and figure out what krypton is. So I look up its atomic number in the periodic table. And so that would be 54. I'm pretty sure about that. Krypton is probably 54. Okay, so what does it become? Well, let's see here. So now we're going to go, krypton is 94. Hold on one second. I'm going to check krypton's atomic number so I get it correct. It's totally wrong. It's 36. I thought xenon might be 54, and it was. So you'll have a periodic table. You won't have to be guessing here. But you got to look up the atomic number. So we go ahead and we do that. Then we go to table N over here, which you will have access to. And we look up krypton. It's undergoing a beta decay. So we go back to table O, which you really should memorize, although you will be given table O on the exam. But if you're taking SAT, you should memorize it. 0, -1. And I write in that particle, 0, -1, beta. And now I do the math. On the top, it's still going to be 85. But on the bottom, it's going to become 37. So now we've gone from 36 to 37, and now we can go back to the periodic table, and we can look up and see what element 37 is. And so when I look up element 37 on the periodic table, I'm pretty sure it's rubidium. Element 37. Let's see here. It's rubidium. I was right. That time I was right. Didn't want to make a second mistake and embarrass myself again. And so here we have rubidium. So what I'd like you to try is I'd like you to try this for thorium. And look up what thorium is, go back to table O and fill in the blanks and see what you get. Don't forget, you can always look on the periodic table for thorium's atomic number. Now, to finish off this video, I just want to show you that sometimes one decay isn't enough to make an atom stable. This is actually a famous series called the uranium decay series. And what you'll notice is that the uranium will undergo a series of decays until finally it reaches Pb, Pb206. Pb206 is stable. It's no longer radioactive, and so the decay series ends there. But they may ask you, like, hey, what happens for the decay from polonium to lead here? So if I start off with polonium, and the number is 218, and polonium's atomic number is 84, well, then that will change into lead. They tell me that. Changes into lead 214. Lead's atomic number is 82. Well, what did it give off? Well, the top is different by 4. The bottom is different by 2. If I look that up, that's an alpha particle. So again, I'd like you to do the thorium decay, and I'd actually like you to do the decay that goes from bismuth to polonium right here. So do this decay as well. Do those two decay equations. We'll practice this in class tomorrow. Thanks so much.